Hello everyone. So today we are going to be looking at the conservation of mass, or it is also known as continuity equation. So it is one of the differential equations for the HBL, hydrodynamic boundary layer. So you can already see that this is a flat surface, or you can say it is a flat plate on which there is a flow, and the free stream is having velocity capital U. So this is the direction of the flow of the flow of the free stream, and due to the flow of the free stream, there is a formation of the boundary layer. And this boundary layer, this is the laminar boundary layer, and then it will reach to the transition, and then it will reach to the turbulent boundary layer. And in case of the turbulent boundary layer, there is also a layer which is named as the laminar sublayer. That is formed like this. So you can see that also. So we are not bothered about those things here. So for making it very easy to you to understand it in a more comprehensive and better way, let us just not take those things into consideration. Okay, so this is the hydrodynamic boundary layer, and inside of that boundary layer, we have taken a control volume, elementary volume that is having, like, this area is A. Okay, control volume, we are naming it A. Okay, so this picture that you can see, okay, this let me show you the picture. Okay, so this picture that you can see over here, okay, this is basically the extended version of this thing. This A, we have just taken it here, we have just zoomed in. All right, so we are naming it called control volume A. Basically this depth, okay, this depth is 1. Okay, so as this depth is 1, so volume will become A, right? All right, so now we can see that this is the velocity small u, as here the velocity is also small u, right? This velocity is inside the boundary layer, and we also know that this velocity small u will become 0.99% of capital U at this point. At this point, right? There was a parabolic. We have seen that thing. There was a parabolic, like this parabolic velocity distribution curve. This was the point at which the value of u is equal to 0, and if you consider this point, this at these points, the velocity is basically rising continuously, and it will eventually reach up to 0.99% here, like this value, at this which we want to track the velocity, right? So actually we are also not bothered about those things, right? That is the concept that we use when we want to define what is boundary layer, and then that is also needed when we are trying to deal with displacement thickness, momentum thickness, or energy thickness, right? Kinetic energy thickness. We have known about delta star, theta, that is momentum thickness, and delta E, which is kinetic energy thickness. All right, so you are also not bothered about that. Let's just get started with this derivation. So as this is u, and this is like this is striking the face dy, right? And this is dx, the elementary volume that you have taken, or perhaps you can say that now it has become equal to an area. So dx is equal to dx is the value of AB, and AD is having the value dy, and u is the velocity, that is the heat, that is the velocity coming from the left face. If you see, if this is the left face, we can name it left face, and we can also name this as right face, like left face is our AD, and right face is our BC, right? So, well, what will be the value at BC of the velocity? That is u plus curly u curly x dx. This is the way how you write it. How we can write it? See, this u has gone through this control volume. It has it has covered this from here to here. It went from AD phase to the BC phase by traveling this distance dx AB. So after reaching here, it was u plus there has been some changes, right? This is how you remember it. U. You write what you write is at first you write u and then plus there has been some changes with respect to dx, with respect to dx, a curly x, or perhaps I can say, and who has been changed? This u. So ddx of u and capital Dx. So this is the standard approach of writing this thing. So this applies in the same fashion. See, from the bottom face, which is AB, the velocity is small v, and it has traveled distance dy from AB or the bottom face to the CD. So like this, from AB to CD, it has traveled, and it has surpassed, or it has traveled the distance which is dy, certainly, right? And what will be the change? How we can write that? See, at first it was v at the bottom face, then it has faced some changes with respect to this distance dy. Who has been changed? This small v, so dy. So this is the way how you write the, I can say, this part which has been changed a little bit. So well, now let's get going. So what are the assumptions in this case? The flow is steady, it is incompressible. The viscosity, fluid viscosity is constant. From where viscosity comes, if you remember, tau is proportional to du dy, or you can say tau is proportional to d theta dt. So from here we can say tau is equal to mu du dy, which is the velocity gradient, right? Or d theta dt is it is the strain rate. It is also possible. So d is equal to mu. So that's it. Okay. I'm just doing this to keep things in track and just reminding those who didn't remember. And no pressure variation in the flow field. That's why we are not taking any pressure in our consideration. And the fluid is continuous and in both of the spatial and time aspect, right? So that's it. So now we have just taken, I have just copied this thing again and taken it here so that I can, write down the equations more easily. Hopefully it's visible now. Okay, so now let's take a look at this phase, at phase AD, at phase AD. Here we have some mass influx, which is like getting in. The value of the velocity is small u. So what will be the value of the mass influx? That is basically rho u dy dt. See how I can write it, right? Let us just derive it. Say how I can write it is. What is mass? Mass influx or the mass flow rate? That is basically something, some mass over time. So it will have the unit as kg per second, right? Here, can you see rho u dy? Rho is having kg per. I'm just writing down. Let it be a little bit more precise so that you can understand it in a more better way. So see, I have written rho u dy. Huh. So what is the unit of rho? That is kg per meter cube into u. It is a velocity. So it is having meter per second. And what about dy? dy is basically meter square. Why meter square? Because it may seem that dy is basically just a length, right? But actually, I have already told you that this is actually a unit thickness. It has a unit thickness. So when you are talking about this phase, this AD phase, this AD phase is basically nothing but something like this. It is something like this. If I want to talk about AD phase, D is here, and this part from here to here, it is basically 1. It is basically 1. So this is dy, right? This is dy. So what is the area? This area is basically dy into 1. So dy into 1, it means this area is basically some meter square. It is having some unit that is meter square. So I can say that this dy is basically a meter square. So from here now I can say kg per, see, meter and meter square and meter cube gone. So we are just left with kg per second. This is actually mass flow rate. Mass flow rate. But what about the mass influx? That is basically mass flow rate times the time d tau. D tau is the short time that we have taken into consideration. So if I'm also talking multiplying d tau here, so there will be into d tau. So this is also going to be having an unit d tau. This is going to be having a unit which is basically second. So this second and this second will be gone. So we will be left with some kg. That is our mass influx. Okay. So I am already done with the explanation that why I can write things like that, right? So let me just make it a little bit smaller so that it doesn't bother you. So we can just keep them in our mind, and I'm also keeping them a little bit there. Okay, so that's it. So now, so this is the mass influx, rho u dy dt d tau. See, from here the mass is entering, so it is having some velocity which is u, and this rho is the density dy. Why dy? Because here this is dy, it is having some certain area, that is and the area, and d tau is the time difference. Then if we want to talk about the mass efflux, change in the mass, which is getting output mass from the elementary control volume, elementary area. So here it is going to be u plus this thing, right? So this is going to be written like this. See, rho. See, we can consider this equation. Okay, so here rho is rho, but this u has been changed in case where it has just got out. This u will be changed. This u. So in place of this u, we are writing basically this part. We can write that, right? This u changes here, as this is u when in case of influx, but this is the velocity of the value of the velocity in case of the efflux. So u plus du dx, curly u curly x, and dx, and dy dt is like written same as it is. Then we have done nothing but just like multiplied this thing and just opened that. So this became our equation number 1, and this became our equation number 2, mass influx and mass efflux. Now for the bottom and the top phase. So in case of the bottom phase, we have the density as rho, but the velocity here has changed into v, so rho v, and here this dx, which through which it is entering, and d tau is the time. So this is the influx, and in case of the efflux, we can write, we can just replace this v with this thing. As you can see already here, that v should be replaced with this value because it has traveled distance dy inside of that control volume, and dx dt, you can see here that dx dt just uh, copied and pasted as it is. So we have written the equations for the influx, efflux. In case of the top phase, like the like phase AD and BC, and also for the phase AB and DC, bottom and top phase, and the left and the right phases. Now, what to do? So, if there is no accumulation of mass in control volume, okay, let me write it down. If there is no accumulation of mass in the control volume, then we can say the mass that entered, that is the total influx, will be equal to total efflux. So what is the total influx? So just total influx will be equation number 1 and equation number, suppose if I want to name this will be okay. So we can just see that this is our influx and this is also influx. So let's add them. So we can write rho u. Let me change the color so that it becomes easy for you. So rho u dy d tau plus rho v dx d tau. I have added this equation rho u dy d tau and rho v dx dt d tau. Okay, and it is the influx. And what is the efflux? I have written in black, that is rho u plus. Okay, let's just write the final output that I have got from here. Rho u dy dt, rho u dy d tau plus rho du dx dy d tau. Okay, and then we also need to add plus this term. Okay, so this term, if I open it and write it here, rho v dx theta plus rho v dy dx theta. Rho v, and also I need to write theta like this. Okay, so now we can do some things. We can like cancel out some parts and we can end up getting something dy d tau. Okay, so see dy d tau and rho u dy d tau, and here you also have rho u dy d tau. See these parts, like if I want to mark them with this color, this part and rho u dy d tau, this part are going to be getting cancelled. And what about the rho v dx d tau, rho v dx d tau? See rho v dx d tau, rho v dx d tau. They are all gone. We are just left with these two terms. So I can write from here that rho du dx dy d tau plus rho dv dy tau is equal to 0. I've just written this equation and this equation. So now by we know we can take rho and d tau common, right? We can take rho and d tau as common. Rho and d tau can be taken as common. Rho and d tau. So they are all actually basically going to be taken common, and then if we send them to the right side, there is 0. So we will be ultimately getting du dx, and we can also get rid of this dy. Wait a second. See dx dy d tau. So dx, I have just forgot to write a dy also. We are also having a dy here. So dy can also be taken that side. So we are already only left with du dx plus dv dy. See dv dy and dy dx. And what about this dx? We had a dx here. Yes, we also have a dx here also. See here we also have a dx. If you just see, we can find it. Where is this equation? I have made a little mistake here. Rho dt. See here we have a dx. So this dx and this dx are all getting out, and we are just getting this equation. Okay. So du dx plus dv dy. So this is the final equation that we have got, is equal to 0. Okay, so this is the equation which is known as the conservation of mass, or you can say that this is the continuity equation. Continuity equation for hydrodynamic boundary layer. This is the equation which you need to write down there. So I think it was quite easy and clear for you to understand, right? So you can start by drawing this diagram, which is the hydrodynamic boundary layer U, and this elementary volume. Then you write this control volume where you're having U velocity on the eddy phase, then that is like going out as U plus du dx dx. So like this, P is going in from the bottom phase, and on the top phase you have the other velocity. Then what you're just taking some assumptions. Then we are just writing the equations for the phase eddy, which is the mass influx. And in case of the phase, it is at phase BC. At phase BC, we are having the mass efflux. So that mass efflux is like this. We can write it like this, and then we can just take it out, rho u and dy d tau, and then rho du dx dx and d tau. So I just made a little like observation that I didn't write it at the first place. So you can write that, so that you don't face any other problem, and later you will see that everything is fine and clear, and you will end up getting this equation as a result. Then we have written for the bottom and the top phase. We have just taken them out, and there is no accumulation of the mass in the control volume. So you can say, this is very important, that total influx is equal to total efflux. So we can just use the equations. We can write the influx in place and efflux in place, and then we can like get rid of a lot of things and just end up getting this equation.